Hi everyone, this is me Ashwani here, back with the NCRT problem solving section of the chapter Electrochemistry. So we have completed the chapter in almost 4 sessions, 4 parts. Hope you have watched all the parts and you're ready to do the problems, to calculate the numericals, to solve the question answers, everything. So you're ready? Hope you're ready. Ready? Ready? Yes. Okay, I'm also ready to do the problems. So the first question is, how would you determine the standard electrode potential of Mg2 plus NMG? Okay, so tell me, you need to tell me, how are you going to determine the electrode potential of magnesium? How are you going to determine the potential? So I've already discussed in the previous session that if you are unaware of the electrode potential of any electrode, in this question it's mentioned as magnesium. If you're unaware of the electrode potential, what will you do? You'll couple it with She. Yes, standard hydrogen electrode. You'll react it with standard hydrogen electrode, or you'll compare it with standard hydrogen electrode, and likewise you'll be able to determine the unknown potential of any electrode. So let's see how standard hydrogen electrode is working. Ready? So let's construct a standard hydrogen electrode first, so that you'll be able to learn what is standard hydrogen electrode in this session itself, in this problem answer section itself. So a She means I'll be using here a solution having 1 mole of H plus ions. Okay, 1 molar H plus ions. You can use any solution having 1 molar H plus ions. In this, I'm using a platinum foil coated in platinum black. Okay, platinum black, a platinum electrode coated in platinum black. To this, I'm bubbling hydrogen gas at 1 bar pressure. Okay, so this is a setup of standard hydrogen electrode. We'll be having a platinum foil or a platinum electrode covered or coated in platinum black, and the solution which I use is 1 molar H plus ion solution, any solution having 1 mole of 1 molar H plus ions. And here I'm bubbling hydrogen gas at high pressure, or 1 bar pressure. Hydrogen gas at 1 bar pressure and standard pressure and temperature condition. In standard pressure and temperature condition, I'm bubbling hydrogen gas. Okay, so this is a setup of standard hydrogen electrode. And now, tell me, what are the specialities of standard hydrogen electrode? Yes, it's of course a reference electrode. Why is it said as reference electrode? Because the standard potential or the arbitrary potential of standard hydrogen electrode is said to be 0 volt. It is assigned a potential, or a voltage is applied or assigned to the standard hydrogen electrode, and it is 0 volt. So whenever an electrode of unknown potential is reacted with standard hydrogen potential, a potential value will be displayed in the setup, and that value will be that of the unknown potential system. It is because that the standard hydrogen electrode is of 0 volt. Okay, an arbitrary value of 0 volt is assigned to standard hydrogen electrode. We'll be getting the potential of the system whose potential value is unknown. Hope it's clear. So if you are unaware of the potential of, in this question, we are unaware of the potential value of magnesium. So just couple it with, or react it with, or compare it with the standard hydrogen electrode, and then we'll be getting the EMF of Mg. So let's see how that is working. For that, I need a magnesium wire. Dipped in MgSO4 solution. So this is going to be one of my electrode, an electrodic solution. The other one is standard hydrogen electrode, the other electrode. So the EMF of this system will give you the EMF of magnesium. So when I noticed the deflection of the galvanometer needle, the galvanometer needle is showing a deflection from the side of magnesium to that of the standard hydrogen electrode. From that, it is very, very, very clear that magnesium is undergoing oxidation. As the galvanometer needle is deflecting from magnesium side to the standard hydrogen electrode side, it is very clear that magnesium is undergoing oxidation, and the standard hydrogen electrode, their reduction takes place. Reduction takes place. So now we need to calculate the standard electrode potential value. We need to calculate the standard electrode potential value. So first of all, let us represent this cell. Anode, anodic solution. This is the Sol bridge. Cathodic solution is H plus, H2 and PT. Okay, this is clear. Now, the total standard electrode potential of the cell is actually E cathode minus E anode, right? But the E cathode value is actually 0. The potential of She is 0. So from that, we can write the cathode value is 0 and anode value is actually E naught Mg2 plus Mg. Okay, so that will be the E naught cell, the standard cell potential. So as to determine the cell potential of magnesium happening, the potential of magnesium, E naught of Mg2 plus and Mg can be determined as a negative of the cell potential. That's all. And this is the final equation to be written in your answer sheet. Okay. Now, the second question is, can you store copper sulfate solution in zinc pot? Is that possible? So check the reactivity, the electrochemical series. Which is reactive, more reactive, copper or zinc? When compared to copper, zinc is more reactive. So is it possible to store copper sulfate in zinc pot? Let's see the reaction between copper and zinc. Zinc, when reacting with copper sulfate, CuSO4, actually zinc displaces copper. So what happens? Zinc sulfate is formed by displacing copper. So copper, yeah, zinc is saying copper, okay, bye. Go. Now it's my position to stand near to sulfate. Okay, so zinc is actually displacing copper because zinc is more reactive than copper. Okay, so it is not possible to store, not possible or impossible to store copper sulfate, CuSO4 in zinc pot because zinc is more reactive than copper. Now our third question is, calculate the EMF of the cell in which the following reaction takes place. Ni plus 2 Ag plus gives Ni2 plus 2 Ag. The standard cell potential is given here, that is to be 1.05 volt. That is 1.05 watt. So how are you going to find out the EMF of a cell when the standard EMF is given? Whenever standard electrode potential or standard EMF is given to you, the cell potential or the electrode potential can be, the cell potential, EMF of the cell can be found out by using the equation E cell equal to E naught cell minus 0.059 by N log the concentration of Ni2 plus divided by the concentration of Ag plus to the power of 2. This equation is known as Nernst equation. What's the name? Nernst equation. Using this equation, you can find out the cell potential if the standard cell potential is given to you. So, E naught cell is already given 1.05 minus 0.059 by N. N is 2. N is 2 here. Log the concentration of Ni2 plus is already given here 0.160 divided by concentration of Ag plus is given here 0.002 to the power of 2, and you'll get the answer as 0.91 volt. This is the answer. So whenever the standard electrode potential is given to you, you can find out the cell potential by applying the given values to the Nernst equation. Nernst equation is E cell equal to E naught cell. Standard electrode potential minus 0.059 divided by n number of electrons log the concentration of the concentration of the substance in the given equation divided by the other concentration. Okay, in this particular equation, it is log Ni2 plus divided by log of Ag plus to the power of 2. We are moving on to the fourth question. The cell in which the following reaction occurs. The following reaction is given here. 2Fe3 plus 2I gives 2Fe2 plus I2. I2. Okay. And the standard cell potential is given here, 0.236 volt at 298 Kelvin temperature. Calculate the standard Gibbs energy and equilibrium constant of the cell reaction. Okay, fine. So, we are asked to find the standard Gibbs free energy, right? You know the equation for finding standard Gibbs free energy if the standard cell potential is given to you. If the standard cell potential is given to you, what is the equation to find out Gibbs free energy? It's none other than minus NF E naught cell, where E naught cell is a standard cell potential, F is a Faraday's constant, and N is the number of electrons. In this given reaction, N is equal to 2. N is equal to 2. And the Faraday's constant is already known to everyone, that is 96500. And the into E naught cell is, E naught standard cell potential is 0.236 volt. Therefore, the standard Gibbs free energy is equal to minus 45.55 kilojoule. Okay, minus 45.55 kilojoule mole inverse. This is a standard Gibbs free energy. It's just very simple to find out. Just substitute the values given in the question to the given equation. The equation is not given, you need to find out. You have already learned from my previous session, right? Standard Gibbs free energy equal to minus NF E naught cell. Now we are asked to find the equilibrium constant. Okay. So if you know the standard Gibbs free energy, you can find the equilibrium constant as well. So what is the equation for equilibrium constant? Delta naught G, standard Gibbs free energy, equal to minus 2.303 RT log Kc, where Kc is the equilibrium constant, R is the universal gas constant, T is the temperature. So as to find low Kc or Kc itself, Kc, the equilibrium constant, you need to find the antilog or log inverse of delta naught G divided by 2.303 RT. So the final answer will be substituting the value of delta naught G, R and T. The final answer will be 9.616 into 10 raised to 7. This is the final answer for the given question. Fifth question is, why does the conductivity of a solution decrease with dilution? Why does the conductivity K, decreases with dilution? As we dilute a solution more and more, why does the conductivity decreases? Let's see. So here I'm considering a beaker, another beaker. I'm having here maybe half the portion of the beaker. I'm having water, which is a solvent here. I'm also having solute particles. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. So to this portion of the solvent, I'm adding little more solvent. Solvent means water. I'm adding more solvent or I'm adding more water means what? I'm diluting it. As we dilute, as dilution is increasing, the volume increases, right? Volume increases means what? Ions per unit volume decreases. Let's see how it is happening. So I've increased the quantity of solvent, means I've diluted it more. So my solute particles turned to be like this. So at a particular portion of the solvent, when I take, there are 3 or 4 solvent particles in beaker 1, solute particles in beaker 1. So when I take a particular portion of the beaker 2, I've diluted it more, so the volume increases and ions per unit volume decreases because I am only seeing one solid particle. So as we dilute a solution more and more, the concentration decreases. Concentration means what? The amount of solute particles present in a particular amount of solvent. So when I see here the concentration in beaker 1, the concentration is very high, as I can see more amount of solute particles in a given particular amount of solvent. But when I look into the beaker 2, as the solvent amount is very, very, very high, as I diluted it more, the solute particles seen in a particular amount of solvent is very less. So as concentration is going down, as it is decreasing, the conductivity K also decreases, because conductivity is directly proportional to concentration. Conductivity is directly proportional to concentration. So as concentration decreases, conductivity decreases. Our 6th question. Suggest a way to determine the limiting molar conductivity of water. Limiting molar conductivity. How are we going to find the limiting molar conductivity of water? Let's see. Limiting molar conductivity of H2O means what? The limiting molar conductivity of H plus limiting molar conductivity of OH minus. Right? H2 is actually H plus and OH minus, a combination of H plus ions and OH minus ions. So as to get the limiting molar conductivity of water, I need to feed into the system. Two substances, one having H plus ions and one having OH minus ions. I need to provide 2 substances to the system, one having H plus ions and one having OH minus ions. So as to provide H plus ions, I'm taking HCl. Okay. So limiting molar conductivity of HCl means what? The limiting molar conductivity of H plus limiting molar conductivity of Cl minus. This is going to be my equation number 1. All set? Now, I need to provide a substance having OH minus ions in it. So for that, I'm taking NaOH. Limiting molar conductivity of NaOH means the limiting molar conductivity of Na plus limiting molar conductivity of Cl minus. This is going to be my equation number 2. So I've already got here the H plus and it's not Cl minus, my mistake. Here my mistake. It is OH minus. Okay. So I've already got H plus and OH minus, so I can produce water. It's H2O from it. But I have 2 extra substances which is unwanted here. That is Cl minus and Na plus. How am I going to eliminate those 2 from this substance or this solution? How am I going to eliminate it? Let's see. It is actually lambda naught m of NaCl. I'm going to provide NaCl to the system. So it will be equal to limiting molar conductivity of Na plus limiting molar conductivity of Cl minus. This is going to be my equation number 3. So as to get the limiting molar conductivity of H2O, you just have to add equation number 1 and 2 and subtract equation number 3 from it. From that, you will get limiting molar conductivity of H plus and OH minus. The molar conductivity of 0.025 mole liter inverse methanoic acid is given here. It is 46.1. Calculate its degree of dissociation. You need to calculate the degree of dissociation and the dissociation constant. You're provided with the limiting molar conductivity of H plus, that is 349.6. Also, you're provided with the limiting molar conductivity of HCOO minus, that is 54.6. From this, we can calculate the limiting molar conductivity of methanoic acid. The limiting molar conductivity of methanoic acid, HCOOH, equal to limiting molar conductivity of H plus what? Limiting molar conductivity of HCOO minus, right? The limiting molar conductivity of HCOOH, that is the methanoic acid, is equal to limiting molar conductivity of H plus limiting molar conductivity of HCOO minus. Now, the H plus limiting molar conductivity value is 349.6, and for the HCO minus it is 54.6. The total value is not this one, 404.2. This is a limiting molar conductivity value. Now we are asked to find out the degree of dissociation. Degree of dissociation alpha equal to molar conductivity at particular solution divided by limiting molar conductivity. Molar conductivity at particular concentration divided by limiting molar conductivity. The molar conductivity at particular concentration is already given here. 46.1 divided by 404.2. The answer is 0.114. Yes, this is the answer. So the equation for degree of dissociation and dissociation constant is already discussed. Those equations are already discussed in part 3 or part 4. I don't exactly remember in which part I've discussed those. So just see those sessions, watch those sessions, and learn how to solve these problems. I've already done a problem with a degree of dissociation, I guess, in the part 3 or part 4. So the second sub-question is, you're asked to find out the dissociation constant. So the dissociation constant, what is the equation for before telling me the equation for degree of dissociation, tell me how is it represented? How the degree of dissociation, how dissociation constant is represented? It is represented as K. The degree, dissociation constant is represented as K. K is actually C alpha square by 1 minus alpha. This is the equation for degree of dissociation, K, and the equation is C alpha square. The symbol for dissociation constant is K, and the equation is C alpha square by 1 minus alpha. C is a concentration. I've already mentioned the concentration is as 0.025. It's already given in the question. So 0.025 into dissociation constant, degree of dissociation 0.114 whole square divided by 1 minus the degree of dissociation 0.114. Okay, and the answer is 3.67 into 10 raised to minus 4. This is the answer for dissociation constant. Okay, the 8th question. If a current of 0.5 ampere flows through a metallic wire, current I equal to 0.5. The time given is 2 hours. 2 into 60 into 60. 2 hours into 60 minutes into 60 seconds. You are asked to find out how many electrons are flowing through the metallic wire. So let's find out the charge first. Charge Q equal to IT, that is 0.5 into 2 into 60 into 60, and the answer is 3600 coulombs. But this is not the answer which we need. We are asked to find out the electrons, the number of electrons flowing through the wire. So if there are 6.022 into 10 raised to 23 electrons, the charge will be actually 1 farad. 1 farad. 1 farad equal to 96500 coulomb. If there are 6.022 in 10 raised to 23 Avogadro number of electrons in a system, the charge will be 1 farad, that is 96500. But here, only 3600 coulombs of charge is there. So we are asked to find the number of electrons. Just cross multiply it. Just cross multiply it. That is 3600 into 6.022 into 10 raised to 23 divided by 96500. The answer, you need to find the answer. As I have no calculator here, I haven't calculated also. So just find out the answer. This is how you have to find it. So the main thing which you have to keep in mind is this. 6.022 in 10 raised to 23. Avogadro number of electrons means 1 farad of charge. 1 farad of charge, or 96500 charge. Our ninth question, consider the reaction. The reaction is given here. What is the quantity of electricity in coulombs needed to reduce 1 mole of Cr2O7 2 minus? Let's rewrite the equation. This is Cr2O7 2 minus plus 14H plus 6 electrons minus will give you 2Cr3 plus 7H2O. We need to find out the quantity of electricity or the charge electricity in coulombs, so as to reduce 1 mole of Cr2O7 2 minus. As we can see in the equation, 1 mole of Cr2O7 uses 6 electrons to get reduced. So the charge, if 1 electron was there, the charge will be 1 farad, 96500. As there are 6 electrons, the charge is 6 farad. That is 6 into 96500. The answer is 5,79,000 coulombs of electricity. For 1 electron, the charge is 1 farad. For 6 electrons, there will be 6 farad of charge or electricity. 6 into 96500. The 10th question is the conductivity of 0.20 molar solution of KCl at 298 Kelvin is 0.0248. The conductivity is given. Conductivity K equal to 0.0248. Molarity is given 0.20. Calculate its molar conductivity. So you're asked to find the molar conductivity, and the conductivity is given here. What is the equation connecting molar conductivity and conductivity? Yes, it's lambda m. The molar conductivity equal to conductivity into 1000 divided by molarity. So conductivity is already given here, 0.0248 into 1000 divided by molarity is 0.20. The final answer is 124, yes, Siemens mole inverse centimeter square. So this is the final answer for the question number 10. Moving on to the 11th question. The resistance of a conductivity cell containing 0.01 molar KCl solution. So the molarity is given here 0.001, and the resistance R is given here as 1500 ohms. What is the cell constant? We are asked to find out the cell constant G star. So we know what is cell constant, right? Cell constant G star equal to ratio of length and area. If conductivity is given as conductivity K equal to 0.146 into 10 raised to minus 3. So now we are going to find out the cell constant. We already know that conductivity K equal to reciprocal of resistivity, right? Resistivity is actually what? Ra by L. 1 by Ra by L. Taking L to the numerator, L by Ra, where 1 by R is the conductance. Reciprocal of resistance is the conductance. So G, and L by A is a cell constant as G star. I'm putting it as G star. So substituting all the values here in G star, G, G star. I'm going to find, or I need to find the G star value. G star means a cell constant value. It is actually K by G, right? Where K is a conductivity, that is 0.146 into 10 raised to minus 3. And G is the conductance. Conductance is not given here, but the resistance is given, right? Conductance is a reciprocal of resistance. It is actually 1 by R. So multiplying it with the conductivity value, 1500, I get the cell constant as 0.219 centimeter inverse. This is the value of cell constant. How much charge is required for the following reductions? So 3 reduction reactions are given here. I need to find out how many charge is required, okay, for the reduction to happen. In the first sub question, 1 mole of Al3 plus is converted to Al. 1 mole of Al3 plus is converted to Al. How can I convert? Or Al3 plus gets reduced to Al. How is it possible? Al3 plus, when accepting 3 electrons, is converted to Al, of course. So how many electrons are used here for the reaction? 3 electrons are used here. So 1 electron means how many farad charge? 1 farad charge. So 3 electrons means 3 farad. That is equal to 3 into 96500. Just multiply it and find the answer. Now moving on to the second sub question. The second sub question is actually Cu2 plus to Cu. The conversion of Cu2 plus to Cu. Cu2 plus gets reduced to Cu. For that I require 2 electrons. Cu2 plus, when accepting 2 electrons, gets reduced to Cu, right? So the total charge is 2F. 2 into 96500 coulombs. Moving on to the third sub question. It's a bit different from the previous two. Third sub question. 1 mole of MnO4 minus gets reduced to MnO2. We are unaware of the state of Mn, right? So as to find the state of Mn, putting X value for Mn and plus oxygen. What is the value of oxygen? Minus 2, right? Minus 2 into 4. The state of oxygen is minus 2. That is equal to minus 1. X minus 8 equal to minus 1. X equal to plus 7. Here, manganese getting reduced to plus 2 from plus 7. Plus 2. See here, it's plus 2. So from plus 7, it is getting reduced to plus 2, right? By giving or by accepting how many electrons? By accepting 5 electrons plus 5 electrons. Okay, so from plus 7 state, when it accepts 5 electrons, it get reduced to plus 2. So here the total charge is 5F, which is 5 into 96500. You can multiply it and find the maximum or total value, the total value of charge. A solution of NiNO3 twice is electrolyzed between platinum electrodes using a current of 5 amperes for 20 minutes. So here the charge Q equal to I into T, right? Current is given here as 5 ampere. And it is passing through platinum electrodes for 20 minutes. 20 minutes means 20 into 20 minutes, right? 20 minutes into 60 seconds. And that is equal to 6,000 coulombs of charge. Keep this data here. What is happening to nickel actually? Nickel is getting reduced at cathode. Ni2 plus, when accepting 2 electrons, get reduced to Ni. Okay. So the total charge here is 2 farad. 2 into 96500. And the molar mass of nickel is 58.7. Okay. So for 2 farad of charge, I require 58.7 7 gram of nickel, right? The question is, you're being asked to find out the mass of nickel deposited. The mass of nickel deposited when 5 amperes current is flowing through platinum electrodes for 20 minutes. So when 2 farad charge is there, 58.7 gram of nickel is deposited. But here, 6,000 coulombs of charge is there. We need to find out what is the value of mass of nickel being deposited at the electrode or the cathode. The calculation to be done is 6,000 into 58.7 divided by 2 into 96500. The mass of nickel deposited is actually 1.825 grams. This is the final answer for this question. Depict the galvanic cell in which the reaction takes place. The reaction is already given here. Zinc plus 2 Ag gives zinc 2 plus 2 Ag. So we have to draw the galvanic cell. You know what is a galvanic cell, right? Galvanic cell is a type of electrochemical cell where the chemical reactions are used so as to produce electricity, or chemical energy is transferred or converted to electrical energy in galvanic cells. Okay, so such a galvanic cell is going to be constructed here using the given balanced chemical equation. We need 2 beakers. In the first beaker, I'm having a solution of zinc sulfate. This is zinc sulfate. In second beaker, I'm having a solution of AgSO4. I'm dipping the electrode. Which is this electrode? This is the zinc rod. I'm dipping another rod in the second beaker. This is the Ag electrode. Now I'm connecting both. to a voltmeter, and also I have salt bridge here. This is a basic setup of a galvanic cell or any electrochemical cell, that you have voltmeter or galvanometer to detect the presence of current flowing. You can also measure the EMF of the cell or the electrode potential using voltmeter. We need a salt bridge. This is the salt bridge. And we have 2 electrodic solutions, that is a cathodic solution and anodic solutions. We have 2 electrodes as well. So in the setup, this is the setup, okay. When you're asked to depict a galvanic cell, you need to depict like this when the equation is given. Or when, even if you're not provided with the equation, if you are provided with the names of 2 electrodes, you should be able to construct the galvanic cell. In this, anode means the place where oxidation takes place, right? Anode means a place where the position of electrode where oxidation takes place. The charge of anode is actually negative. Cathode means where reduction takes place. And the charge is positive. So here zinc is getting oxidized and Ag is getting reduced. Okay. So which electrode is negatively charged? The answer for the first sub-question is given here. Anode is the electrode at which oxidation takes place, and zinc is undergoing oxidation. So the anode is having negative charge. Okay, negative charge. Cathode is having positive charge. The second sub-question is the carriers of current in the cell. So in the solution, okay, in the electrolyte, ions are the carriers. Ions are the carriers of current. Now in the wire, which wire? In the conducting wire or the connection wires from the electrode to voltmeter or from electrode to galvanometer. In that wire, ions are not the carriers of current, but electrons are the carriers of current. Individual reaction. The third sub-question is individual reaction at each electrode. At anode, oxidation is taking place. At anode, oxidation is taking place to zinc. So zinc will turn to zinc 2 plus 2 electrons minus. At cathode, reduction takes place to Ag plus 1, Ag plus 1 electron minus gives Ag. These are the two reactions taking place at anode and cathode. The 15th question is, define conductivity and molar conductivity for the solution of an electrolyte. So what is conductivity? Conductivity K is actually the reciprocal of resistivity, and resistivity is represented as rho. Resistivity, this is resistivity. Resistivity is represented as rho, RHO. Okay. This rho means actually it is 1 by Ra by L. Rho is actually Ra by L. Resistivity is equal to Ra by L. Taking L to the numerator side, L by Ra. Where 1 by, this can be rewritten as 1 by R into L by A. That is 1 by R is equal to conductance. Reciprocal of resistance is equal to conductance G, and L by A is a cell constant, that is G star, represented as G star. This is conductivity. Now talking about molar conductivity. Molar conductivity lambda M equal to K into 1000 by M. K into 1000 by M, where M is a molarity and K is a conductivity, and lambda M is the limiting the molar conductivity, not the limiting molar conductivity. Molar conductivity is equal to conductivity into 1000 by M. You can either define lambda M as such in the form of equation, or else you can define it as well. Molar conductivity means the conductance of solution having electrolyte, having 1 mole of electrolyte placed between electrodes separated by unit length. So when there are two electrodes separated by unit length, and when there is an electrolyte having 1 molar concentration, then the conductance of that solution is known as molar conductivity. Okay, you can either define it like this, or you can either write the equation and specially mention the symbols used, where K is a conductivity, M is a molarity, and lambda M is a molar conductivity. Now coming to the 16th question. In the button cells widely used in watches and other devices, the following reaction takes place. The reaction is given here. Determine Gibbs free energy and standard electrode potential, E0, for the reaction. Also, we are provided with the cathode potential and anode potential. So as to find the standard cell potential, the equation is E0 cell equal to E0 cathode minus E0 anode. The cathode value is 0.34 and the anode value is minus 0.76. So the total value is 1.10 volt. This is the standard cell potential. And the second sub question is Gibbs free energy. Gibbs free energy. Delta naught G equal to minus NF E naught cell. The equation is minus NF E naught cell. We have already found out the cell potential, standard cell potential value. And here N equal to 2, and substituting 96500 into 1.10 volt, you will get minus 2.12. Wait. I'll just write it a little bit bigger. Minus 2 into 96500 into 1.1 volt. So the final answer is minus 2.1 23 into 10 raised to 5 joules. Joules because we are asked to find out the Gibbs free energy. The unit of energy is joules.